Let us prove the following theorem. Given a sequence of real numbers and E and S up star as before, remember E is the set of numbers X in the extended real number system, such that there is some subsequence S and K that converges to that number X. That is, E is the set of all subsequential limits of the sequence, possibly including plus and minus infinity. Okay. Then S star, which is what we call the lim sup, that is the supremum of the set E. Okay. This is lim sup of the sequence. In this setup, S star is the only number, the lim sup is the only number such that it belongs to the set E, and both conditions. If there is any number bigger than S star, then there is some capital N such that if N is bigger or equal than capital N, then Sn is smaller than X. Okay, this means, again, we saw a similar picture. So if we have our sequence that accumulates somewhere here, and this is our, here we have our S star, okay? And I pick some X that is bigger. What the theorem is saying in the second part is that after there will be some time in the sequence, it will keep jumping. It may accumulate and then jump with an outlier. Okay, boom. Again, close, 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 back, close, 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 outlier, and so on. But after some point, it will never go past X again. That is what number 2 is saying. Okay, and of course, there is an analogous statement for the lim inf of the sequence. All right. So with this setup, let's go ahead with the proof. So here, to prove part A, there are 3 cases. The 3 cases are if S star is, let's say, negative infinity. This means the supremum of E is negative infinity, and that is the lowest it can be, right? So that means that E contains only negative infinity. Okay, and if that is the case, then for every real number m, Sn is going to be bigger than m for at most a finite number of values of n. Okay, here what I'm saying is Sn actually converges to negative infinity. Okay, because otherwise there would be more accumulation points. Okay, so this is the first case. Let's move everything, create some space here. There we go. The second case is if S star is plus infinity. Okay, so if it's not bounded above, that means that Sn as a sequence is not bounded above. And by definition, that means that there has to be a subsequence such that S and K converges to plus infinity. Okay? Because if it didn't, then Sm would be bounded above. Okay? So these are the easy cases. Now we need to tackle the important one, let's say, which is when S star is a number. Okay, let's say it's a real number. S star is in R. Okay. In this case, we want to show that S star, which is the supremum of E, actually belongs to E. Okay. To belong to E means that there exists some subsequence S and K such that S and K converges to S star. Okay, and this has to be a subsequence of the original sequence. So we need to construct it. Okay, so let's do a picture here again. Let's say that we have our S star here, and the sequence can converge. Remember, it can go beyond once in a while. Okay, but after some, eventually it will have to accumulate around the limit point. Okay, so this is what we want to see. This is what we are looking for. Now what we are going to do, we are going to consider a neighborhood here, okay, which is an interval. And what we are going to do is we are going to choose some n0, okay, such that Sn0 is different from S star. Okay, and once we do that, we put delta, the distance between S star and S0. So let's say this is our delta, and I picked, let's say this one is our Sn0. N0. There we go. Okay. Now what we are going to do, we need to create a sequence. So what we are going to do is choose every term of the sequence, the subsequence, in the following way. We choose N1 such that there is some term Sn1 that is smaller, that is within a distance smaller than delta over 2 from S star. And then I can choose N2 such that S star, there exists some term in the sequence that is within delta over 4 from S star, and I keep going. And in general, I'll pick Nk such that S and K is within delta over 2 to the K from the S star. Okay, so here we are decreasing and decreasing. Now, you may be wondering, why do these S and K that I'm saying they exist? Why do they exist? Well, notice what happens here. Otherwise, here what we are saying is that for every, let me write it carefully. We are saying that for every K, 1, 2, 3, and so on, there exists some nk such that S star minus snk is less than delta over 2 to the k. Okay, here notice that this nk has to be bigger or equal than k. Okay, otherwise there would not be a space. Now the negation is there exists k such that for every n bigger or equal than k, S star minus snk is bigger or equal than delta over 2 to the k. Okay, so when we are saying this, we are saying that when we go beyond a certain term in the sequence, okay, here I meant n, not nk. When we go beyond a certain term in the sequence, then all the terms stay away from S star. Okay, so we will have here our S star plus delta divided by 2k, and here minus delta. And this is saying that somehow the points, there are a few inside, but then most of them are outside. Okay, so what does this mean? This means that S star is not close to any subsequential limit. So it's not a least upper bound. It is an upper bound, but we can improve it. Okay, we have that margin delta divided by 2 to the k that we could reduce the bound. Okay, so that proves part A. Now part B, here we just suppose that there is some x bigger than S star, as the theorem says. Okay, and for this x, then Sn bigger or equal than x for infinitely many n. Okay, here we are assuming the opposite of what we want to show. Okay, so in this case, if we have infinitely many n for which Sn is bigger or equal than x, then there exists some subsequential limit, some y in E, such that y is bigger or equal than x, bigger than S star. And this means that S star is not the least upper bound. Okay, and the last thing that remains to show is the uniqueness. Okay, that there is only one with these two properties, A and B. So let's say there are two. Always the uniqueness goes the same way. Assume there are two P and Q that satisfy A and B. Okay, let's say doesn't matter. Let's say P less than Q. Otherwise, we would say Q less than P. The proof will be the same. And now let's take X such that P and Q are on either side of X. Okay, X is in between P and Q. Now, because P satisfies B, that means that there exists a bunch of Sn less than X, okay, for n bigger or equal than n, okay. But if this is the case, okay, if all the Sn for n large enough are less than X, then Q cannot satisfy A. Okay, that means Q cannot belong to E, because what is happening here is that we are trapping most of the sequence on the left of X. So therefore, since Q is on the right of X, it cannot be a subsequential limit.